Soon after this event was discovered, scientists realized that the delta C13 might be explained by the release of carbon depleted in C13 to the atmosphere. And there were a few different ideas. One possibility is that a giant volcano emitted an enormous amount of CO2, causing a drop in the delta C13 and warming the climate. Volcanic CO2 from the mantle is typically around -6 parts per thousand, or -6 per mil. You can do a simple mass balance calculation to figure out how much mantle CO2 you would need to add to the ocean and atmosphere to drop the delta C13 of the ocean by 2.5 per mil. This turns out to be about 30,000 gigatons of carbon, a huge amount, almost the same size as the total ocean reservoir today. But this simple calculation doesn't take into effect the changes in ocean pH and ocean chemistry that come about as a result of the added carbon dioxide to the atmosphere. When you add so much carbon dioxide to the atmosphere, the pH of seawater changes dramatically. And this changes the partitioning of carbon isotopes between the different carbon reservoirs in seawater. In the end, it turns out that this actually drives an increase in the delta C13 of calcium carbonate. And so this effect is large enough that you can never add enough mantle CO2 at -6 per mil to cause a 2.5 per mil drop in the C13 of seawater. Because as you add more and more of this carbon dioxide, the delta C13 of calcium carbonate starts to rise because of the effect on pH. So mantle carbon dioxide is pretty much out of the question. Another possibility is adding organic carbon, which has a delta C13 of around -25 per mil. The mass of organic carbon required to create a 2.5 to 3 per mil carbon isotope excursion would be about 5,000 to 6,000 billion tons of carbon, a huge amount. Think about it in terms of the carbon cycle today. That would be like adding almost 10 times the total terrestrial biosphere to the atmosphere in a very short amount of time. Interestingly enough, it's not that different from the high carbon emission scenario we saw in David Archer's calculations. If we burned all of the carbon from coal and oil and gas over the next few hundred years, we would release about 5,000 gigatons of carbon as well. We'll come back to that point later on. Another idea was that the carbon that created the PETM isotope excursion came from methane. Now, methane is interesting because it's much more depleted in carbon-13 than regular organic carbon. It has a delta C13 somewhere between -60 and -90 parts per thousand. And so it only requires maybe 2,000 or 2,500 gigatons of carbon to produce the same 2.5 to 3 per mil excursion. This is a much cheaper way of getting the excursion. And Jerry Dickens and colleagues in the mid-90s proposed that it was the release of methane at the PETM that actually created both the warming and the delta C13. Where did they find so much methane? Remember, 2,000 gigatons of carbon is still an enormous amount of carbon, equivalent to the entire terrestrial soil reservoir today. So this is no small feat. But Dickens and colleagues pointed to an important reservoir of carbon that they thought had been overlooked by studies of the carbon cycle. This was methane hydrates, a very unusual chemical form of methane that's really an ice molecule. You can see a depiction of the molecular structure of methane hydrate here. It's a metastable phase that has many molecules of water forming a cage-like structure around a methane molecule in the center. It contains so much methane that even though it's composed mostly of water, you can actually light it on fire as a solid. Methane hydrates occur naturally in parts of the Earth where there's a large amount of methane and water, and the temperature is low and the pressure is high enough for this methane hydrate to form. So methane hydrates are unstable in the surface environment. They only occur at high pressure and high temperature and will rapidly decompose to methane and water if they were released. Methane hydrates occur today all along the coastline of continents in water depth below about 700 meters, where organic matter is slowly converted to methane by bacteria and archaea. These microorganisms are constantly producing methane, which is being released to the ocean and then getting oxidized in the water column. But in places where there's enough methane concentration, the methane reacts with water at those pressures and temperatures and forms methane hydrate solids. And you can see methane hydrates sometimes on the sea floor. In many cases, we can only see these methane hydrates through seismic images, as the hydrates reflect seismic waves much more effectively than the surrounding sediment. Exactly how much methane hydrate exists is still fiercely debated. Estimates range from 1 to 2,000 gigatons of carbon to as much as 10 or 20,000 gigatons of carbon. And some groups, including the Japanese, have tried to develop technology to exploit methane hydrates in certain places as a resource of natural gas. So Jerry Dickens proposed that the release of methane hydrate, perhaps driven by a warming of ocean temperatures, might actually lead to the PETM itself. Let's look at that hypothesis and see if we can reconcile that with the observations. In this figure, we see the Delta O18 record, which shows the abrupt warming across the Paleocene-Eocene thermal maximum, as well as the Delta C13 record, which shows the abrupt release of carbon. Now, what would happen if we had this drop in C13 caused by an abrupt release of methane hydrate? If methane hydrates destabilized and the methane was released to the atmosphere, we might expect a very abrupt warming, because methane is, of course, a very powerful greenhouse gas, much more powerful than carbon dioxide. So we would expect this very, very fast warming, but the challenge is that methane has a very short lifetime in the atmosphere. Currently, it's about 10 years. Even if you released a huge amount of methane and overwhelmed all of the sinks for methane, which are mostly oxidants in the atmosphere, over a time scale of hundreds to certainly 1,000 years, all of that methane would be converted to carbon dioxide. So 2,000 gigatons of carbon released as methane and then converted to carbon dioxide over less than 1,000 years would have a residual carbon dioxide left in the atmosphere of roughly 100 parts per million. So you would only raise atmospheric CO2 by a relatively small amount. You would still have this long tail of the carbon cycle that we've discussed, but it would be a tiny, tiny amount, hardly sufficient to account for the warming that persisted for the better part of 100,000 years or more. In contrast, if we try to explain the PETM by the release of a much larger amount of CO2 from the oxidation of organic carbon, we see a much better fit to the observations. If 5,000 gigatons of carbon as organic carbon were oxidized during this event, we would see atmospheric CO2 levels roughly triple from a background level of maybe 500 or 600 parts per million to a peak value of somewhere between 1,500 and 2,000 parts per million at the height of the event. We would expect carbon dioxide levels to increase, and then we would expect the temperatures to slowly subside on the same timescale as carbon dioxide was removed by the silicate weathering process, roughly 100 to 200,000 years. And that's more or less what we observe. So overall, the observations of the PETM are probably best explained with a much larger release of carbon dioxide from organic carbon than a smaller release from methane hydrates. So methane may be the cheapest way to put the least amount of carbon in to explain the warming and the C13 excursion, but it doesn't actually fit the timing that we observe in the sediments. So overall, the oxidation of 2,000 gigatons of methane increases atmospheric CO2 over the longer timescales by only about 100 parts per million. It's inconsistent with a 5 to 6 degree increase in global sea surface temperature. But just as important, remember that we saw this huge drop in carbonate content of the sediments. This is due to a big ocean acidification event. We believe that the removal of calcium carbonate from sediments seems to require more like 4,000 to 5,000 billion tons of carbon. So methane release couldn't explain the acidification of the ocean that we observe all over the world oceans. So the bottom line is we need more carbon than the methane hydrate hypothesis can provide. The methane hydrate hypothesis may be the cheapest amount of carbon. That is, it can explain the carbon isotope excursion with a relatively small amount of carbon, but it's inconsistent with the other observations that seem to demand a much larger release of carbon to produce the acidification we observe. So where did all this organic carbon come from? Well, one idea is that it came from sediments in the North Atlantic. Right around the time of the Paleocene-Eocene thermal maximum, there was a huge volcanic province emplaced in the North Atlantic, connected with what is now the Iceland volcanic region. So much lava came out at this time that some scientists have speculated that the hot lava reacted with organic carbon in the sediments to cause the release of huge amounts of methane and carbon dioxide, and that this might have led to the drop in the delta C13 we observe in the carbonates. A problem with this hypothesis is that the timescale of the emplacement of these lavas probably was too long to explain the abrupt 10,000-year nature of this event. If you did have huge amounts of lava reacting with organic carbon, you would expect that it would continue and not be so tightly confined to this 10,000-year period that we see in the C13 record. The C13 record is very clear that the release of carbon was short-lived over 10,000 years, and then slowly the carbon cycle recovered over maybe 100 to 200,000 years. The emplacement of these lavas probably happened over a slightly longer timescale, more like hundreds of thousands to maybe 1 million years. Another observation that challenges the volcanic hypothesis is that when you look at sediment cores that have drilled through these lavas, what you see right next to the lavas in the sediments that surround them is that they have just as much organic carbon as any other sediments in the sediment column. So this depletion of organic carbon doesn't seem to exist. Those lavas may have heated up those sediments, but it didn't get rid of all that organic carbon. Another hypothesis that my student John Higgins and I proposed about a decade ago is called the epicontinental seaway hypothesis. The idea here is that the Paleocene was a very different time than the modern carbon cycle because large areas of the continents were covered with epicontinental seas. Sea level was about 100 meters higher, and this meant that large parts of North America, Africa, and Asia were covered with shallow seaways. These shallow seaways would have been rich in nutrients and a perfect place to bury large amounts of organic carbon. Our idea was simply that if you had a large epicontinental sea with sediment rich in organic carbon, that some sort of tectonic event might actually cause the isolation of this event. In particular, we were thinking about the collision of India with Asia. We speculated that a large epicontinental seaway north of the collision zone between India and Asia, where current Afghanistan is today, might have been the perfect place to bury huge amounts of organic carbon. But once India started to collide with Asia, then the edge of that epicontinental sea would have become uplifted, and ultimately that epicontinental seaway would have been isolated from the main ocean. This would have been a threshold event, so essentially either the epicontinental sea was connected to the ocean or it wasn't. As soon as it was cut off from the rest of the ocean, the dry subtropical environment would quickly evaporate the water in this seaway and turn these organic-rich muds on the ocean floor into soils that have very little organic carbon today. In terms of time scale, this would have happened very, very quickly. The current Red Sea, for example, in between Africa and Asia today, has a net evaporation of almost 2 meters of fresh water per year. So you can imagine a shallow epicontinental sea, only tens of meters deep, if it were ever isolated from the world ocean but was still in the subtropics, might evaporate in just a few decades, leaving behind dry ocean bed full of organic carbon, of very organic-rich sediments, which would quickly get oxidized over the next few thousand years, releasing a large amount of CO2 to the atmosphere. This hypothesis explains why we might have seen these events at that time when there were still epicontinental seas, but why we don't see these events later on in geologic time once sea level has dropped and the epicontinental seas no longer exist. By the way, this hypothesis also explains why smaller events like the PETM that occur in the early Eocene might be triggered by similar events where smaller epicontinental seaways dried out. These events aren't as large as the PETM, but they're similar enough to suggest that a similar mechanism might be responsible. The most troubling hypothesis for the PETM might be that none of these things were responsible, but in fact that the PETM was caused by a set of carbon cycle feedbacks triggered by a smaller event that we may never put our finger on. At this time, we know that there were large peat deposits on the continents associated with the higher sea level and these epicontinental seas. There were large swampy areas that had lots of organic carbon. And it's possible that some event, whether it was triggered by a volcano, the release of methane hydrate, or the drying up of an epicontinental sea, set in place a series of feedbacks that released a lot of the soil carbon stored at this time and ultimately led to the PETM as we know it. If this is the case, if there wasn't a particular event responsible for the whole carbon, but this was just a runaway carbon cycle feedback, that in some ways is the most troubling for our current predicament. Not only would we never be able to identify what the actual cause of this event is, but it says something very troubling for our future. Think about all of the carbon stored in soils in the Arctic, for example. Is it possible that by burning fossil fuel to the extent we have today, we might actually put in place a series of positive feedbacks that release more and more carbon, leading to the same kind of 5,000 gigatons of carbon that was released around the PETM? It's interesting to go back to the David Archer figure and think about the role of the PETM as an analog for our future. If we think about the very high carbon scenario where we burn all of the fossil fuel, or alternatively, there's a large carbon cycle feedback like the release of carbon from the Arctic that leads to 5,000 billion tons of carbon cumulatively emitted to the atmosphere over the next few centuries. We see this calculation that David Archer did where the carbon dioxide climbs up to about 1,900 parts per million and then stabilizes at around 1,000 parts per million for tens of thousands of years. Temperatures would increase by about 6 degrees and stabilize there, again, slowly coming down only on the timescale of silicate weathering, turning carbon dioxide back into calcium carbonate and removing it over hundreds of thousands of years. This is not that different from what happened at the Paleocene-Eocene thermal maximum. We think that a large amount of organic carbon was released as CO2 to the atmosphere. This acidified the ocean, causing a huge dissolution event of calcium carbonate all over the ocean floor. We think carbon dioxide levels tripled or maybe even quadrupled, and that temperatures all over the Earth warmed by at least 6 degrees Celsius. So this high emission scenario of David Archer is really not that different from what happened at the Paleocene-Eocene thermal maximum. Our records don't record the transient increase in CO2 over the next few thousand years. That's too short a timescale to be recorded in the sedimentary record. All we see is the slow, steady state of around a 6-degree warming and the stabilization of temperatures there for about 100,000 years, which is what we expect will happen if we burn all of the fossil fuel we know about today. If we compare the size of the Paleocene-Eocene thermal maximum to the maximum warming in the early Eocene around 50 million years, we see that it's probable that the short-term warming around the PETM just exceeded the maximum warming in the early Eocene. But of course, this short-lived PETM event only lasted for about a few tens of thousands of years and then slowly cooled over about 100 to 200,000 years, whereas the warming at the early Eocene persisted for millions of years, allowing animals and plants to adapt in a very different way. Interestingly enough, we don't see a huge mass extinction at the Paleocene-Eocene thermal maximum. Of course, many of the plants and animals and algae living in the surface ocean already went through a big extinction just 10 million years earlier at the Cretaceous-Tertiary boundary. So they were still recovering from that huge mass extinction that killed the dinosaurs. At the Paleocene-Eocene thermal maximum, what's interesting is that the only organisms that seem to go extinct are the benthic foraminifera, these benthic organisms that grow on the bottom of the ocean. They show a huge mass extinction and turnover right at this time. they were not very much affected by the Cretaceous-Tertiary extinction. One reason for this could be that the Paleocene-Eocene thermal maximum caused a big stratification in the ocean, that by heating up the surface of the ocean so quickly, it slowed down the circulation and caused an oxygen crisis in the deep water. Another possibility is that the acidification of seawater affected some of the benthic organisms in a large way, and that the dissolution of calcium carbonate was a difficult biological stress for these sorts of organisms. Some people take comfort in the fact that the Paleocene-Eocene thermal maximum didn't cause a huge mass extinction in surface-dwelling organisms, given that it's an analog for what might happen over the next several thousand years. Of course, we have to be careful with that analogy because the climate was already warm in the Paleocene-Eocene thermal maximum, and it got warmer. That's very different than our current climate, which is a glacial climate, getting as warm as it may be in the next several thousand years. Cold-dwelling animals that are adapted to those sorts of environments simply have nowhere to go as the Earth warms and ice disappears. Another important point is that biological diversity today is probably threatened more from human land use changes than by climate change itself. What climate change is going to do over the next few thousand years is push many of these organisms already threatened by human land use to the brink. Back at the Paleocene-Eocene boundary, the animals and plants only had this climate change to deal with. They didn't have the additional stresses of human land use changes as well. One final point is that the Paleocene-Eocene thermal maximum, we think, occurred more slowly over about 10,000 years. So it's possible that the plants and animals living at that time had an easier time adapting to the abrupt change in climate because, in fact, it wasn't that abrupt. It occurred over 10,000 years. It was a very big change, but it occurred slowly enough to allow them to migrate. What we're doing today is happening so quickly over just a few centuries that it will be very difficult for most plants and animals to adapt.